will introduce you. One second. Great. Okay. Good morning, good evening for everyone, and we are here to see a presentation, a plenary presentation from Andreas Andreou. So let me introduce Andreas. So Andreas is from Johns Hopkins University. He's a professor and he's co-founder of the Johns Hopkins University Center of Language and Speech Processing. The research in Andreas' lab is aimed at brain-inspired microsystems for sensory information and human language processing. Notable microsystem achievement over the last 25 years include contrast-sensitive silicon retina, the first CMOS polarization sensitive imager, silicon rods in a standard foundry CMOS for single photon detection, and large-scale mixed analog digital associated processor for character recognition. Significant algorithm research contribution in pattern analysis and machine intelligence include the vocal track normalization techniques for speech recognition and heteroscedastic linear discriminant analysis, a derivation and generalization of Fisher discriminant in a maximum likelihood framework. So it's a pleasure to have Andreas here. He was one of the first guys to support EAMTA in the early years. I remember him visiting Cordoba in 2007. So it's a pleasure to have you, Andreas, and please go ahead with your presentation.
Well, thank you so much,
Benjamin.
And Pedro.
The Pedro Cost.
I am I'm honored to be invited to give a presentation about work that we have done. And this work involves multiple people from Argentina, at least 4 people, as you will see from my presentation, involved and still involves. And I hope soon we'll have this meeting in person, maybe in Cordoba, maybe in Buenos Aires, maybe in Bahia Blanca, maybe in Brazil.
We hope that too.
Yeah, so this is my presentation, and I will talk about neurochiplets. This is really a new way about thinking about chiplets. Is a new way of thinking about systems, building systems. And I just wonder if anybody has heard the word chiplets in this group. Just put your hand up, and now I'm just checking. Well, okay, so I will explain to you what that is. But first, let me begin to say this is really the team, a very happy team at that time. Sitting down is Gaspar Tonetti from University from Bahia Blanca. The fellow in the pink shirt is Thomas Figlioli, that is from Argentina. You can see our fearless leader Pedro here. And right, so we've had this collaboration for a long time, and who is not in the picture here is Martin Villamur, which is still with us, but I guess that day he was out. I will put him in the next picture next time. So let me talk a little bit first about AI. you have several presentations, and you have had people giving talks about AI. And then I will give you a little bit about an introduction to Brainwave, which is really a bio-inspired architecture for cognitive computing. Then I will describe NanoAbagus 2.5D, the chiplet-based bio-inspired system that we designed here. And I will show you, I will finish my presentation with some of our latest results. So artificial intelligence, what is intelligence? Is the ability to learn, understand, or to deal with new or trying situations, the ability to perform computer functions. And so this is really something that is very popular these days. We hear it in the news every day. And artificial is based on human contrived and based on a morphological characters, not necessarily indicative of natural relationship. This is really, when we talk about artificial, you understand what it is, but these are really the definitions in the dictionary. So let's look at now at AI and the three waves of AI. I'll give you a little bit of a history of where we are and where we came from. So the first wave of AI was in the 80s, was basically using handcrafted knowledge and rule-based systems. This enabled reasoning over limited domains and poor handling of uncertainty with no learning. And perhaps the best known example of AI at that time, it was a chess playing machine, the IBM Deep Blue chess playing computer that you can see on the right side. I should point out that this IBM Deep Blue, in addition to the standard IBM hardware that had in it and software, had actually some specialized chips to do the search that helped it really beat human chess players at that time. And of course, programming environments at that time is Lisp, Maxima, and you had companies that tried to make specialized machines to really tackle the AI of that era. Then we have now the second wave of AI. And the second wave of AI started actually about 20 years ago. It is really about statistical learning of low-dimensional structures from high-dimensional data. And today, we associate that with deep neural networks, deep learning. And this is really, the whole world is going crazy about AI, mostly because of advances in deep learning and deep networks. And perhaps one of the most remarkable achievements of this technology, it was their ability to play the game of Go with deep neural networks and tree search. And that's from a small company in UK, United Kingdom, that subsequently was bought by Google. And the software environments to actually do this deep learning are TensorFlow. You have which is a Google standard software that everybody's using, Caffe, the Microsoft Cognitive Toolkit, and the Intel Deep Learning Toolkit. And a lot of these deep learning systems run on specialized GPUs or TPUs, and even embedded systems on HTPU, which is a small Raspberry Pi-like processor board that you can buy for about $100, $90, I don't know how much these days. And you can run these deep neural networks and AI. So let me actually go through some of the work in AI to bring things in context. In the early 90s, we envisioned that, and I started my career, that we'll make a chip that actually we can talk to you to, and you will understand. And a little article was written there, and the illustration of the article now is the logo, has been the logo for my lab. And now, essentially, we recognized at that time, I mean, this is really 1990, that's 1990, that would be 30 years ago, right? So for computers to become useful tools for the masses, they must be redesigned so they communicate not with the keyboard, but directly with their operators and the surroundings. Think of Alexa today or Siri. This is really the kind of things that you want to do and you use every day. At that time, this was a crazy idea, but we're thinking about it. So we start working to really develop the technology, and we build custom chips. And on the panel on top, you see Philippe Poulik and Mark Cohen, and on the middle picture, Kim Strobin, a friend and a colleague that unfortunately passed 2 years ago. And on the bottom picture is Guadena Boagen, who was a graduate student at that time at Hopkins, and he was involved with our system building activity. And now he's a professor at Stanford, building silicon brains like we do. At that time, let me remind you that what we had as a compute environment, it was a Pentium Pro. That was fabricated in 0.5 micron technology with 5.5 million transistor, 150 megahertz front side bus, 60 megahertz clock, 150 megahertz clock and front side bus, 66 megahertz, 3.3 volts, and the whole system had 64 megabytes of RAM and 5 gigabytes of hard drive. Of course, though, at that time, the most powerful processor was a DEC Alpha 2164A, a very powerful system, a few less transistors, but with built-in cache on the die, and about the same power profile. What makes actually Intel Pentium Pro interesting, and in the context of this discussion, it is because perhaps we can argue that this was really the first chiplet-based design. Anybody knows why the package is like this? Someone wants to suggest? Okay, the package is in this shape, and it's elongated in one side because in the package here, you have two dies, and they are connected to each other on the same package. So you have a package, and you have two dies. One die is a cache, and the other guy is a processor. And it was recognized then that, hey, if you can get the performance, if you cannot lose performance, makes sense. The economics of the fabrication and manufacturing makes sense to really do things modularly. And so this modular design went away for many, many, many years with system on chips, and is coming back. So, of course, for those who are new to this business and chip design, at that time we used RSIM, Magic, and SPICE. And at that time, again, we recognize that one of the most powerful way of thinking about computing and the brain is really combining processing and memory in the same structure. And at that point, we designed a very simple circuit for those who are circuits oriented, and we built a chip, a mixed signal chip. And the simple circuit uses just 4 transistors to both store the memory, store the state, a binary state, and also perform the exclusive OR operation. You may be wondering now, how can you do that? Well, the way you do that basically is you bias lines B and BI. It's a current mode circuit. It's a current mode cell. And what happens now, the state of the cell is preserved using this cross-couple P-type pull-ups. And the leakage current, a very, very little leakage current that keeps this circuit alive through the transistors, the N transistors here. Now, by biasing the lines B and B bar here at different voltages through a circuit that I show above that takes the current out, we can make a winner takes all, and we can find the max, and we can compute this max operation of the exclusive OR of every cell in the array. And of course, at that time, we also realized that we should exploit the statistics of the problem. And we use, in this case, it was Hamming distance classifier, character recognition, laid out on the grid, much like everybody's doing today, MNIST. And in this system, we could actually compete with the best algorithm running on the Pentium Pro and on the DEC Alpha. The best algorithm for per classification was 600 microjoules on the Pentium Pro, on the DEC Alpha. And for the chip that we built, it was 100 nanojoules. So we are about 6,000 times better than solving the same problem that a powerful computer could do that. And the reason that it worked like this is because we incorporated memory and processing in the same structure. And by doing so, we didn't have to move data from the processor to the memory, to the GPU, to the cache, to the GPU, back to the processor, and back to the hard disk. So the idea of actually doing processing embedded in a memory structure, again, is a recurrent idea that we'll also see later towards the later part of my presentation. So this chip was built in 2-micron CMOS technology and operated from 5 volts. Let me now talk about the third wave of AI, which is really what we're trying to do here is go beyond deep neural networks. And to go beyond deep neural networks, we need to start thinking a little bit outside the box, or more like how humans perform these functions. So we have sensing that actually, this is kind of a diagram of the approach. We have sensing where we are converting word to signals. We have perception where signals are turning to information in a rigorous way. And then we have information feeds knowledge, and in which is in the form of a contextual model. And the AI machine actually is involved to learn abstractions to represent the knowledge. Once you, and this is a continuous loop, you're continuously learning new knowledge representation and building new models as you acquire data, something that deep neural networks today don't do. You go and you collect all the data and you train your model and you just, you do inference. Maybe you'll do adaptation. Maybe you can do some learning, but it's really very limited what you can do. And it's fundamentally different than what I propose here. Once you actually have the knowledge and perception feeds the knowledge, you reason, which is really where you do inference, where you take the information and you convert into actions, and actions then are what drives behavior. And this is, for example, where you have the machine driving a car to really to produce a self-driving system. So let me now introduce you to the architecture for cognitive computing, the bio-inspired architecture, which we call brainwave. So the brain, of course, is what you use to listen to this presentation and try to make sense of what I'm trying to say and trying to understand my Greek accent, speaking English, someone which is not native speaker. And so comparison is some of the most powerful computers that we have today. And the IBM Blue Gene is one of those computers. And of course, these computers take lots of energy and they require very sophisticated cooling systems. And the reason that I like to show this picture, which is kind of a little bit old, is because it points out to the design of a system. You see the front face that is slanted? It is slanted because that is part of the design for flow of air in the system, how the system gets cool. It's not just they decided they wanted to have a slanted front face to look cool. It is actually functional, and that underlies where most of where the challenges of modern computing in data centers, which is really consume a lot of power, and we need to really figure out how to solve that problem. So, having said that, what I want you to remember about this slide is that both the brain and physical machines exist in three-dimensional physical space, but can deal with problems in hyperdimensional spaces. And the reason is that I say this is because from the early days of building powerful supercomputers like the connection machine, it was realized after they built it that that machine was only good or could do very well at solving problems which naturally map into a three-dimensional space. Field problems, physics field problems, where you have nearest neighbor interactions are good. Deep neural network problems were not very good mapped. They were not very well mapped on the connection machine. So as we actually think about architectures and systems to solve problems and how they compare to the brain, what is remarkable about the brain is really the fact that it does exist in a three-dimensional space, but it can effectively solve problem in hyperdimensional spaces. And I think that is really why the brain is so amazing. So we set up a program, a research program articulated about 7 years ago in a paper that we wrote with Andrew Cassidy, Julius, and myself to design silicon brains in the nano-CMOS era. We recognize that there is some parallels between brains and machines, silicon machines, but those parallels we should abstract. And to do that, we thought that it would be good to really address the building of brains in bio-inspired computing systems by looking at 3 levels of description. On the top, we have theory, computational theory. And really, if you want to think about what kind of theoretical theory does one need to build an architecture to do computing, which is brain-inspired, it's really all about parallel processing under physical constraints, delay, energy, and variability. That's it. So as we think about developing theories, computational theories, we need to understand that what makes the brain so amazing is that it is a parallel processor, and yet not a parallel processor abstractly derived as a set of equations of a piece of paper, but rather as a physical machine. And therefore, delay, energy, and variability in the components play a huge role. Then we can actually start thinking about algorithms and architecture. And this is really where we have the brain architectonics, and we want to think about multiprocessor architecture. We have dynamics. How do we map the dynamical aspects of the brain behavior into silicon machines? And we have spike-based processing, most information processing in the brain. occurs in this domain where we have discrete events in a continuous time called spikes. We need to really turn that around and use them in synthetic systems and try to map those ideas into ideas that are really natural for silicon systems. And finally, on the bottom, you have the physical implementation. And we know that the brain is organized in a three-dimensional structure, three-dimensional organization. And until recently, most silicon systems have only been two-dimensional. Most system on chips that you had until the last 4 years, except experimental chips that we and others have built, have been two-dimensional. And I argue that the 3D dimensionality of the brain is really one of the aspects that gives the brain this capability. And we saw that happen in silicon once we went from 2D to 3D, actually 2.5D, and that's exactly also what the brain has. The brain is not quite the 3D, is a collection of two-dimensional architectural microstructures organized in a way that minimize communication costs, and that brings that again naturally to the concept of a chiplet that I will discuss later today. So we begin to start thinking about that, and we look at state-of-the-art machines that are available at that time. The Spinnaker system and Spinnaker 2 developed at Manchester by Steve Ferber, and of course, the most popular one was the True North from IBM, an architecture, a neuromorphic architecture that was designed to really model and capture the behavior of the brain. And as you can see here, this is really the first paper that they wrote describing the chip at IBM. There's about 40 authors in this paper, and you can see the first author is Andrew Cassidy. This is really the graduate student in my lab that developed the theory and the framework how to design and optimize computer architecture, and was a co-author on that paper in the previous slide. So he went on to IBM and he kind of led the design architecture of the final chip together with Rodrigo Alvarez and John Arthur and Paul Merola and others. We were graduate students in Quabena's lab. So that chip was developed and everybody used it, and it was, by all accounts, very successful. So what's next? Well, what we discovered on that chip is that, which was mostly digital, that chip, because of design considerations and the time to produce something, it was a completely digital chip. So, but it did use event-based information processing, and it did use what I would call calculating computing by counting, which is really very, very similar to how ancient Greek and Chinese used to actually do math using the abacus or the Salamis tablet, which was predate, the modern computing architectures. And so that was the genesis of the nano-abacus CMP, which is really, this is really the presenter here at in Athens, at the museum depicting the Salamis tablet, which was really an early way of ancient Greek using to do mathematical calculations. The Swanpan, spelled Swapan, is the abacus of Chinese origin, back to 190 CE book of Eastern hand dentistry. And the Soroban is an abacus that was developed in Japan, and it is derived from the ancient Chinese Suan Pan. And finally, Yupana is an abacus used to perform arithmetic operations back into the time of the Incas in Central America. So we see that all cultures, whether Greek, Chinese, Japanese, American, had thought about devices to actually do computations, and mostly what they did is really do these computations by counting. So we thought we'll take these ideas and bring them to modern technology, make chips that use counting, make them about 100,000 times smaller than the original devices, and that was the genesis of the Abacus project. So when you actually want to build an architecture to do computing, you really want to do computing at the energy limit. And to do that, we'll use basically the what I have here in the yellow block, which is anisochrons, technically called anisochrons pulse time modulation, or what I would call discrete valued continuous time representation, or spikes, where information is encoded in the interval between events, but the events are actually quantized in value. And in doing so, you can actually do fine analog processing without worrying too much about preserving, about noise and preserving the accuracy of your computations. So another idea that is central in really computing at the energy limit is actually doing the computing and the state holding at the same place. So minimize communication, global communication. So if we can actually have a cell that can do storage, integration, and multiplication, that is really great. In this case, we can use charge and capacitor arrays, and we can actually connect the capacitors together to do a vector addition, and we can use a very simple AND gate to do a scalar multiplication if we have events in time. And we can encode and decode that using mixed signal representations, and all the computations that we do in the arrays and the cost for the computations are amortized in this mixed signal computation. And that is how we actually get the efficiency. So let me summarize the design methodology that we've been using. We have precision on demand. The accuracy of the computations can be configured before runtime by setting the number of events for every circuit, and that defines the precision. This is a very old idea. I mean, and it is surprising that it gets reinvented every few years. Intel created BMX instructions to do graphics where you actually could take a 60-bit processing unit, floating point or integer processing unit, and turn it into an 8-bit processing unit. And more recently, ARM discovered that they can do the same thing, and they came up with the, if you're familiar with the ARM Cortex U55 architecture, where now they are, or the Helium architecture, where they're really doing something similar. They are taking the scalar units in a microcontroller, and they are turning it into a vector unit to facilitate DSP and to facilitate machine learning. So that is really cool. And that is really something that anytime you can do that, we should be doing that. Digital hardware, we design digital hardware that can be operated at ultra low voltages at the limit. About 400 millivolts is really what we do. Analog hardware that can be operated, again, at very low voltages at the limit. About 500 millivolts is what we do. we have a way of representing data directly as probabilities, and that allows very sophisticated computations to be done in the time domain in this discrete value continuous time representation or spiking representation, and that is really has been very, very useful for some of the AI computations in probabilistic inference that we want to do. Of course, we need to really design nice circuits for probability encoding and decoding. And then we need to have standard flows, cadence, synopsis, and metrographics. And unfortunately, standard flows are not really good at designing such large-scale mixed signals. And of course, anytime we can get standard libraries, IP, ARM, or superflash non-volatile memory that is integrated with the circuits that we designed, this is really a good thing to do. And let me now actually, oops, the title, the arrow showed up before the slide. Let me actually talk about something which is really also I touched upon at the beginning, which is 2.5, 3, and 3D, and the importance of that working in 3D architecture. Okay, remind you, why 2.5, 3D or 3D? Why? Because brain exists in three-dimensional physical space but can deal with problems in higher dimensional spaces. We know that as we go from 2D and from 2D to 3D, we can save in energy. What you see here in this little diagram by a paper by Andrew Cassidy is really the cost of a bit, the energy cost of a bit to travel a distance going all the way from 10 nanometers on the left here to about 100 meters on the right. And what you see on the table here and with the index is really the physical medium which the bits uses to travel. And you can have bits can travel within a small circuit, within a transistor actually itself. They can travel within a functional unit. They can travel within a chip. And this is roughly the energy that it costs for a bit to go as you go from a single transistor, which is somewhere about here, to the end of the chip, which is something about 10 to 14, and to the board level, to another chip, which is 10 to the minus 12 joules. So even though this is not shown here, there's a big gap, which is about 2 orders of magnitude going from intra-chip to another chip to the board and going back to the chip. So that is really, that's a gap that that indicates that going 3D or 2.5D would be beneficial because we don't need to really move the bits in a two-dimensional space, but we can move laterally up and create a 3D stack. And I always want you to remember another thing from my presentation. When we talk about computing, remember, doing actually the computations is free for practical purposes. Flops are free, let's free the flops. What does it mean, free the flops? Free the flops means let's use the flops that are free to actually solve useful problems. And that is where communication comes into play a role. And that is really where the challenge is. As I indicated, and I'm blowing the slide here, 3D is important because it allows us to actually go, I'm repeating a little bit more with more details here, from within using a silicon via to replace electrical switching across a single die. Even going from a circuit at the end of the die to the board, it takes about 2 to 2.5 orders of magnitude more energy than actually if you push your data in D, which is a 3D silicon via. So Silicon vias allows wafers to be stacked on top of each other and interact with each other. And of course, also you have the crossbar, which is resistive ReRAM. This is really the memristor technology that we've been seeing recently. And you can also have embedded DRAM in a 3D structure in FinFET technology. This is the IBM 3D stack. And even more exotic technologies where you can actually have embedded memory using magnetic memories that are sitting on top of a silicon structure. So we are seeing the proliferation of technologies that are using sort of the 3D structure in the technology itself. We want to take it to the systems. We did design some experimental system. On the left, you can see the chips. What you see here is our processors, the little in a carriage here that are sitting on a. The processor is a little on the left side here is a little black square that you see on the top here, and these sit on these bigger other rectangles, which are basically interposer in a 3D memory stack. So what we have here is a processor that is stacked on a DRAM, which looks like an HBM memory today. This was back about 10, 15 years ago, before HBM, in a sense. The stack under the processor here, and this processor here is a series, is like a series compute server that we designed in the lab. It is really this technology what evolved to become the HBM. Unfortunately, making stacked chips on DRAMs, it wasn't a viable solution, and we're going to see later where this emerged. The 2.5D architectures emerged to solve the commercialization aspects of integrating processing with high bandwidth memory. I should point out that I was introduced to 3D by Hiroaki Kurino, a colleague, collaborator, and friend that passed very young. Really, he was working in Japan in Professor Koyanagi's lab, who is the inventor of the DRAM cell and they were working on 3D systems, and he was working too hard and really literally died because of overworking. I mean, it was really sad. Anyway, we made a lot of progress since then, and we built neuromorphic 3D systems. We have a silicon retina. You can see the silicon retina in a just 130 nanometer technology that work. You can see the imaging. This chip integrates photoreceptor, and it can do both imaging at the single photon layer, but also it can integrate. So it is essentially a single infinite dynamic range silicon retina, and also working with the good folks in Argentina. This is an experimental chip that we designed in collaboration, which is a 3D morphological processor, 130 nanometer process. This is probably one of the very few chips 3D chips, experimental chip, that were designed in academia and actually work. And you can see the chip here. You can detect. It has detectors in one layer. The bottom here, the bottom tier, it has the top tier has the array of cells, the photodetectors, and some of the data buses to move the data and do the computation on the periphery. And then on the bottom cell, You have the registers and the latches where you actually state holding elements or local caches. This is very similar to the architecture that I presented before, but in a very more primitive way, where you have processing on one layer, and on the bottom layer, you have memory. And you can see here data from this chip that they were collected, I believe. This is really about 10 years ago, or maybe 8 years ago. So going beyond 3D, as you can see, 3D architectures are hard to do. And so there came the idea of a chiplet-based silicon on chip, system on chips, where today monolithic, you have a system where you can have the processor, you can have memory here, you can have a radio, you can have a floating point unit, you can have an encryption processor, all in the same die. What if we actually could make a Lego-like system where we build little modules and we plug and play on a standard platform, which is universal? This is what we call a chiplet approach. AMD actually came up with this idea again about 10 years ago. And again, this is really before all the craze and before the Tensor TPU and before everything that is happening today. This is from a presentation that I attended, AMD, where they envision they're going to have an interposer where you're going to have power and data buses, and you're going to have memory, and you're going to have a CPU, you're going to have the cache memory, and a field programmable gate array, and you're going to have accelerators. And accelerators is basically, in this case, is graphics accelerators. They're called today GPUs. This conceptual description materialized through an experimental architecture that it was predate the Vega architecture of AMD. The Fiji architecture was kind of the first interposer architecture using this chiplet-based approach. And the reason that this is effective is that modular design is much lower cost than system on chip. Today, the Ryzen Threadripper, it has actually quite a bit of memory, 32 megabytes of quad memory, and it is really basically a chiplet architecture. Again, today, the state of the art, we use cadence synopsids, and they're still not good enough. So at the same time, we are part of a project. That presentation was given in a meeting where people are proposing ideas and projects. We had a project with DARPA, and we proposed our own chiplet architecture where we are proposing to have, this was really ambitious, a silicon interposer. It will have a Xilinx Zig 7100 FPGA. It will have a DRAM, a 3D architecture, memory architecture, a precursor of the modern HBM that is used in GPUs and computers today. And so we proposed this project, and we started it, and we start working on it. Here is actually our interposer. This is today probably the biggest interposer ever built. It comprises 4 reticles, standard reticles, 32 millimeters by 25 millimeter reticles stitched together. This is actually a layout, a cadence layout of the superimposed with the components. You have the memory, which is really the 3D stack. You have the FPGA for high bandwidth communication. In this case, we're using SerDes interfaces, 8 lanes at 12 gigabits per second. And we designed 3 chips, 3 chiplets that actually will go on this interposer. This is not a picture. This is not a fake picture. This is actually a real imager of the fabricated interposer. And you can see one of our chiplet design will go here. Here on the right side, you put the Xilinx FPGA in a die format, and here in the middle, you have the bandwidth memory. I should really say something about the DRAM chip, and this is actually a picture of one DRAM chip. It consisted of 16, a stack of 16 DRAM arrays, each one for 4 gigabit arrays. And it has an aggregate of 16 terabits per second bandwidth within the stack. You have an I/O controller, and you have a DRAM controller fabricated in 45 nanometer technology, and it has an I/O controller, and this memory has 64 lanes of 32-bit ports. So you actually can read and write in this memory in 64 in chunks of 32 bits, and you have 64 ports. So this allows so much flexibility in allocating resources and data structures that makes it a very, very powerful memory device, or total aggregate throughput about 4 terabits per second, and a total memory of 64 gigabit or 8 gigabytes. So going back to the architecture, imagine now having a system with 8 gigabytes of cache memory, because effectively that's really what you have here. You have the memory integrated on the system. Unfortunately, the sad part of the story is that the company that used to make these devices, they could only make 1 or 2 or 3 experimental. They actually did. And this is a real picture of the device they fabricated. And eventually what happened, the technology was sold to Hynix and the intellectual rights, and to Samsung, who start producing reliably now the HBM architecture. But think of this DRAM 4 with a 4-port packet switch I/O controller. You actually had 4 ports, and you can actually push any data from any of these 4 ports to the memory. This is really a rather crazy computer architecture component that unfortunately never took off because it was too expensive to fabricate. Nonetheless, we're designing with this. We designed a chiplet architecture that actually had the interface to this memory. It had a 2 NOCs, a first-tier communication fabric to push fast data in and out of the chip, 8 rings, which are shown here in black, and it had a second-tier communication fabric, which is a mesh network, that is shown here in blue, that allows the processors to communicate to each other. We had a Cortex-M0 processor for controlling and supervision and testing, and we had another Cortex-M0 with a little bit more memory for allowing the configuration and for doing some computations that could not be handled by the computational arrays. We built a chip. This is the chip. The chip has 12.72 millimeter by 15.27 millimeter in 55 nanometer Global Foundries technology. These are the 4 chiplets. Each chiplet, they all look the same, but they have different processors inside. You have the same interfaces, physical interfaces, high speed, low bandwidth here, SPI on the bottom here. These are the M0 core. These are on the bottom here, or on the top there. You can see the ARM processors. We have 4 designs, so we can populate any processor standardized architecture chiplet. And we even wrote code that actually could program these chiplets, and for doing different computations, mostly actually linear algebra and morphological processing, which is really something that Pedro's group in Argentina has advanced. So, and here is a list of the capabilities of these chiplets in terms of second wave AI and third wave AI. We can actually do neural networks, and we can run deep neural networks, but we can actually do more than that. We can actually run differential equations. We can do model-based inference. We can use learning with dynamical systems. So it goes beyond, it went beyond the deep neural network. So what you saw there in those 4 chiplets was not something that is just doing deep neural networks, but thinking and doing beyond deep neural networks, probabilistic inference, computing with probabilities, and doing cognitive computing the way we envision it will need to be done in the third wave of AI. Well, here is the same picture. Here is the wafer with all the picture, with all the chiplets. And May 2017, the wafers came back and we tested them. And what you see here is the same people now, but with sad faces. Notice Pedro's face. Oh my God, Pedro was really, really very unhappy. And so was Andreas.
Oh my God. Is that me?
Yes. And so is Andreas. Andreas is crying. So Gaspar and Thomas and Pedro they are the Thomas, Pedro, and Gaspar, the Argentinian in this group. And that day, Gaspar delivered the sad news that the chips on this wafer will never work. And that was the end of this project. Well, thank goodness we have the good friends here at Northrop Grumman that actually help us. Said, okay, guys, you spent 6 years working on these chips. We really need to help you. So with their help, financial and practical, we redesigned the architecture. We call it now the C-Think chiplets. This again, a whole reticle. We fabricate a whole wafer. We have the C chip and the Think chip, and they have the same architecture. However, instead of a ARC processor, now we use a Silicon 5 or High-5 RISC-V S7 processor. It has a full floating point unit here. We also have here a Silicon 5 RISC-V S21 processor. We changed the interface. Martin Villemur designed an amazing general purpose I/O and high-speed interface that is designed to run at 1 gigabit. The NOCs were designed to run at 200 megahertz. This is 65 nanometer process. We fabricate the chip, and here is a chip now is working. Here is the board, the test board with the chips. And this chip, this is really our test environment. We can actually say now we have our chiplets working. They're packaged and tested on this test board. They're running at 200 megahertz. The NOCs, the processors are running at 200 megahertz for these chips. And we can perform, we can perform multiply, accumulate, measured, not estimated. It was simulated about 25 femtojoules per op. We have simulated 22. We actually measured 25 femtojoules per op, which really gives you something of the order of teraops and milliwatt per milliwatt. So this is really an extremely efficient chip. And we are, as we speak, checking it. And with this, I can say now that we still have back now the happy faces of the group, and more people now looking happier because now the chips work. And finally, I want to thank Northrop Grumman, Luis, and Isidoros, and Sergio for really not only financially helping us, but also helping us design the chips, verifying the chips, and now even creating the boards and the test boards that we get these things to work. So with this brings me to my final slide of my presentation, and I will open the floor to questions. You must have some questions. Pedro, what's up? Hi, Pedro. Man, good to see you.
Good to see you. I was listening to you. I was picking up the kids, but
yeah,
I was able to hear
this is you. Hey, look, that looks like you a little bit.
Here's the fake Pedro.
That's the improved version. He's younger. He has more hair.
Yes.
More hair. That's only advantage. More hair.
So anyway,
I have a couple of questions.
Yeah.
So one thing of the chiplet, what I don't see the evolution is the way we are stacking chiplets or placing in a plane, because at the early years of 3D or 2.5D integration, we have the option of some bumps at that level to connect to interposer or through-hole via.
Right.
And all those was very limited in capacity to connect chiplet to chiplet. So how is that nowadays?
Okay, so if you look at the interposer here, this is really the design that we did with very limited resources. In fact, at that time when we were designing the interposer, there's no tool to actually.
That is the second question.
Yes, there was no tool. Yeah, we wrote our own tools to actually do the routing on the interposer and design this chip. And it was really a tool that Philippe did. There's even maybe a paper on that, or maybe we never published it. I mean, we should have published that at that time. But this chiplet, this interposer here, uses 8,000 standard C4 pads. Okay, and we did it because of conservative design. We did not have the capability at that time to reliably stack, put pads smaller than a C4, which is about 80 micron. Today, we can do reliably, very reliably standard stacking on interposer, the commercial ones that are being done, or experimental one, I should say, which are about, I would say, they're called microbumps, about 10 micron. And so that is really where we are, or 4 micron even, aggressive designs. And that is really where we are. Both TSMC and Intel, they have developed technology, standards. The EBIB standard in Intel allows, and is open, allows chips to connect between chips on an interposer. And also TSMC has developed some standards that can allow you to actually integrate beyond this. This is really 10 years old. Okay, this is 21. We started this project in 2014 or something like that, or 13, when we proposed it. So this is really technology that's about 10 years old. What I'm showing here, it's still relevant, but that old. Did I answer your question?
Yeah, so you see a lot of evolution in the tools to do the integration of chiplet and interposer, and the fabrication of them.
Yes, in fact, once at the time where we finished designing the interposer and went to fab, remember this interposer is huge. It's 4 stitch reticles. You cannot do that today. Nobody has tools to do that. So that was even more crazy and more conservative. Okay, and it worked. We actually tested it, and the interposer actually, we get reliable communication across stitched reticles. For those who don't know what stitched reticles are, all the chips today in fabrication are designed in a standard frame. so to speak. And that standard frame is about 32 millimeter by 26 millimeter. Hey! And so, and the stitch, right, if you want to make something bigger than 32 by 64, which we wanted, obviously, you need to actually do lithography and align the two reticles so that they actually right next to each other, so lithography can be done across. So at the time that we're finishing the project, and Global Foundries, you could download a toolkit, a design toolkit from Global Foundries to fabricate interposers. So you can actually do today.
So it's much more standard, and you can rely on the
Yes.
on the fabs to do your project.
Yes, and so the interposers today don't need to be silicon; they can be organic, in fact, and lower cost. This is really kind of a high-end system approach, something that you see today in the TPU, in the Tensor, in the NVIDIA RTX 8000 cards, RTX, the state-of-the-art GPUs from NVIDIA, AMD, and TPUs. They all use interposer standard Ryzen. By the way, interestingly enough, Intel, in their 5 Xeon processors, they were perhaps the first company to actually use interposers in a serious way in a project. Slightly different, but so going back to what I said, interposers don't need to be silicon. They can be organic. They can be flexible. The idea of a chiplet, and so for example, we are designing chiplets now that use SPI interface. Okay.
I see.
SPI, quad SPI. In fact, where is, I don't have the picture here. So all you need basically is a quad SPI interface, which is what, 11 wires, plus VDD and ground, plus biases. So 16 wires. And you can send data at high speed. We're also designing chiplets that use a PCI Express lane. PCI Express lane again is 2 and 2 plus 2 clock. Again, is 8 wires. By the way, the Edge TPU, the chip that actually is on the little Raspberry Pi board, actually communicates with the world with a single lane PCI Express.
I see.
So
yeah.
Yes.
I see. The last question related to this integration chiplet is how it is, in general, is speaking, how it solves the power. I mean, if you place high-end computing and DRAMs, etc.
Okay.
Then you
that
concentrate.
question, yes, that question has always been a question everybody asks. Okay.
Yeah.
So, first of all, chiplets so far, as I showed in this picture here, let me select. Oh yeah, I guess I should really share my screen for a second. As you see from this, okay, sorry, I didn't realize I wasn't. From this picture here, the 3D stack here is mostly DRAM, and the end power in the DRAM is very little. So what you, if you're actually gonna put if you're gonna make a chiplet, okay, so let me just show you, let me just go away for a second. Do you see this? Oops, no. Let me.
Zoom is filtering a little.
Yeah, I know.
Have to remove it.
I'm back. I want to show you a demo.
Maybe on your T-shirt, maybe we can see.
No. Okay. Do you see?
Yeah. There is.
Yeah, you see
there
this?
We see it. Yep.
This is actually a Vega 64 AMD card, GPU card. This here is a GPU, and the two little squares. We don't need this. Let me stop sharing my screen. Yeah, I was going to make
Yes.
and I'll put this here.
There.
Okay,
That,
this
there
is
is
a
good.
Vega. I took out the heatsink, and you see
Yes.
the interposer. You can see the big square is the GPU, and then you can see the little other squares is the HBM, the memory. So what happens now, because they're backside down and they're the same height, the heatsink will actually sit here on top. So it will take all the heat out.
Yes.
The advantage of this is basically, oh, that's kind of funny. I can see the picture, your picture in the, or Pedro's picture
Pedro
in
is there.
the, I can make you too in the image. The advantage of this is that you can buy the chips, these particular chips, because I know, because this card I used to work, and I broke it apart to take pictures. It's a Samsung HBM and looks like the 3D stack. So the same thing. I mean, for the high-end systems, there is cooling solutions, including now solutions that actually involve, because it is a 2.5D direct dimension. You're still working in a 2D, but you actually have a modular approach. And I think that's the beauty. And that's what the brain does too. It gets faulted, allows for interconnects, high bandwidth interconnects. So, I mean, we are designing the chip that I just showed on the board. We'll be working next year to design that with in the Intel 22 nanometer technology with the standard EBIB interface, chiplet interface, going down to now much finer pitch, so you can actually stack them.
Yeah, I was thinking that this a new industry. I mean, we have previously the IC industry separately to the, I don't know, board design, and so we have something in between that actually in your country is not much developed. And I don't know if the tools guys are doing specific tools for that, or we are reusing the board design tools to do this, or the IC to do this.
I think here is the key. And I want to give a plug here to one of my students that invented this idea. If you're going to be doing high-speed serial interface over boards or interposers of various varieties, you can go two ways. You can go parallel and put a lot of wires where you depend on really fine pitch lithography, 5 micron. You cannot do a PC board 5 micron, but you can do, you can design a chiplet that has bigger bonding paths and you can actually put on a PC board, on organic fancy PC board. Or you can go serial. If you're gonna go serial and you want to really you want to control the performance of the system, you have to do learning on the interface, on the SerDes. So the SerDes comes up and calibrates itself, and it doesn't matter what board, who designed the board, or who designed the system. Okay, this idea sounds like a very simple idea to go parallel to serial, but adding the machine learning on the calibration and all they did in the first design is a very simple adaptive equalization algorithm, a Wheatrow-Hopf algorithm. It's something that at the first, it was worth $400 million. This is really the company that Kuwei Yang, one of my students, started. And that's the idea. They basically built a chip that will take parallel and serialize and put on any board, and it will work on any board they put it. It doesn't matter. You don't need to worry about the lines, the width, the thickness, the electromagnetics. So that's what you need to have in mind, that you really need to make adaptive algorithmic constructs, machine learning on the chip, for example, to really make sure that even cheaper fabrication can actually accommodate the products, because at the end, price matters.
Yeah, makes sense.
Anyway, this is really, by the way, the same thing is happening. I mean, the evolution of this idea is in the device that you are watching me. If it uses a display port. Most likely your monitor uses a display port. Large number of the chips designed by a display port is manufactured by Analogics. Cuvée Young, the same guy, went on to start Analogics that makes all the display port interfaces and whatnot. And again, the idea is here, you want adaptive equalization to really make your chips work regardless of the board. And by the way, I don't show this on the chip design, but a lot of the work on this chip here, let me get a picture here. A lot of the, let me display again, just a second, give me a second. Share screen. If you look at this this image, on every one of these chips, there's a big area. Let's say in the middle, look at there's 4 chips here, and you have in the middle, there is the area that is all this layout here in the middle on the left side, which is a high-speed interface for the, let me see if I can point to this, if I can actually annotate. Basically, all of this here for the chips and this here for this chip here is really the high-speed interface design that actually learns to calibrate itself to be able to communicate on the interposer. That's a really crucial thing. A lot of the design went to actually make that circuit to adjust the timing and calibrate the timing so all of the lines communicate properly on the interposer. Anyway.
Makes sense. Yeah, you have SerDes on all the boards.
This is not SerDes. This is parallel ports, but they still need to be calibrated.
Yeah.
They are really actually, they're not SerDes. They're not SerDes. They're not parallel. There are 96 ports here, but each port serializes the data about 10 bits. So it is a serial interface, but it's not SerDes. It's low voltage here. Yeah, it's just a standard. That's how they designed the interface. Yeah, but still, you need to calibrate. You need to learn the interface. You need to learn the parasitics, and it does it when the chip turns on automatically. It will go and do it.
Yeah, I understand.
Yes. Cool. Anyway, a lot of the details.
I don't know if we have more questions, Pedro.
Quick comment. Really happy to see the final chip working. It's very rewarding. I don't know if people get an idea of all the complexity that it's inside. There's really a lot of systems. There's a network on chip that communicates everything. It's extremely complex. So I wanted to ask you, Andreas, if you can comment a bit on how was the effort to test this. I imagine it's something that you don't see every day.
No, you don't. I actually, you want to ask the right question, but you asked the wrong question. How was the effort to verify this before fabrication? Because once you had verification and test vectors, it was testing it. We designed the board and they plug it in. And literally in 2 weeks, the thing was running because all the code was written to verify things.
Very good. So how much time it took to verify?
Pedro, I think it took 2 man people, Northrop Grumman people.
Wow.
They had 2 people working for verification, and we worked together, but it was really, because once you have everything, and we had a complete model running on FPGA. So
of the whole system?
Of the whole system.
Oh my God.
So what happened, the chip came back, we first connected to we connected the FPGA to the board. They made the board, you see the board. And then they start probing and things start working. I mean, we had a few glitches, like the serial port was not syncing, but once a few mistakes, it was programming the wrong frequency on the
Mm-hmm.
PLL to support the serial port. When that was figured out, in 2 weeks, we are running computations in this array.
Wow.
Not just code. I mean, okay, I should really point out a little bit what involves here. The system has it has 3 interfaces. It has an SPI and a UART. It has a general purpose IO, 32 ports at 100 megahertz, and it has a high-speed interface, 64 at 1 gigabits per second. So far, we have tested the UART, the octal SPI, and the general purpose IO, because for the purpose, it's enough for us to get going. So you push data on the S7 and the S21. These guys can push data on the nodes. On the node here, at every node, there is a reduced instruction set controller that actually is programmed to do operations within the core, okay? So that works. Martin wrote Python code to compile that into instructions, and he is refining that code. And then even within each array, there is a Pico controller. Instead of a finite state machine to actually, I didn't tell you what's inside here. Every one of these is kind of a computational DRAM. It's a pseudo DRAM. Pedro knows what it is, from the previous project. And at some point, you'll be on the paper, Pedro, too. I mean, when we write a paper. I mean, I think it's a lot of people worked on. I mean, it's literally the respinning of the Soroban, but fixing everything that we did wrong. But it works, man. The chip, the processor runs at 200 megahertz. It has 1 megabyte of RAM, SRAM. So this actually is an Arduino compatible chip. We can actually run Arduino code on this thing.
Oh, that's pretty amazing.
Anyway, this is where we are, man. Martin did an amazing job. Martin is the Argentinian, still with us and going to Pedro now next month.
And capturing him.
Pedro, I really need to publicly thank again Northrop Grumman for teaching us how to actually design complex systems like this, because this is not something it's very difficult to do. Once you've done it once, we know what to do, but anyway.
Very complex.
Yes, but Martin knows. Now Martin is the man.
Yep.
Anyway. By the way, Gaspar, also the other Argentinian, went on to work for Apple. Apple recruited him because Apple is designing everything. Every component of their chip is designed in-house. They don't use any IP from outside. Anyway.
Yep.
Okay, guys.
Benjamin? Okay, Benjamin is not here.
Yeah.
Okay.
It is. I think nothing else from my side. On YouTube, we have some question we had, but was related to we discussing earlier, like the communication, and then the power dissipation and the synchronization between the. Someone asked if we consider asynchronous design techniques, delay insensitive or relative time analysis.
Okay, that's a very good question. Part of this system uses asynchronous circuits to interface with the synchronous design. And for example, the camera that we have, the imagers, they are totally asynchronous and using delay insensitive circuits. Unfortunately, the flow to do both is not completely done. We are excited because we are about to begin a new project with Northrop Grumman, and Kwabena Boahen is involved. Pastor, from Stanford, and we'll be doing a lot of this. We'll be doing it using now truly asynchronous design methodology. It would be a good lesson for us, but that would be the next 4 years. But we have the funding and we have the support to act, and the people, they know how to do it, which is Quadena.
That's good.
Anyway, again, I want to thank Northrop Grumman for being really an incredible partner and understanding on this project, and really for helping take those phases and making them happy again.
Yeah, I remember that time.
You remember that time, man?
Yeah.
A lot of unhappy people.
Yeah. On my side, if I may, let me thank Andreas, because he gave us me and Pablo like 20 years ago.
Oh yeah.
The chance to do microelectronics, and now most of the young guys that you see here, Benjamin, Jose, Nico, Gabriel, Joel, the guys that are putting together the school this year and have been helping for the last 3, 4, 5 years. It's another layer. It's just keep helping. Yeah. So thank you, Andreas, for everything.
Oh, it's been a pleasure. It's been amazing. And I show the chips that you designed, the morphological, the 3D morphological, and Martin and the other Martin,
Mm-hmm.
This is really amazing. And Pablo, oh my God.
Yeah.
Gee.
Yeah.
Yeah.
Okay, thank you again, Andreas.
Okay, thank you, guys.
Thank you so much.
Yeah.
Thank you very much, Andreas, for supporting.
Bye, everyone.
Bye, guys, and good luck, and hopefully soon in Argentina. Hey, Pedro, I'm going. I'll talk to you later. I was thinking about stopping through Austria. I'm going to Cyprus in May, but I'm going through
you're
Frankfurt.
Welcome.
Yeah, I'm going through Frankfurt.
No. Okay.
Yeah. You can come and visit though for Easter.
Okay.
Anyway.